In this video, we'll be discussing section 2.3, acceleration velocity models. We're going to begin by recalling Newton's second law, which is surely familiar from a previous calculus course. Recall that the vertical motion of body with mass m near the surface of the Earth, while neglecting air resistance here, is modeled by Newton's second law, which is F equals ma. And what we're going to do here is we're going to restate a, which is acceleration, as the derivative of velocity. So here's your m, here's your a, and here again, we're talking about the force due to gravity. So we'll denote that as Fg. Throughout this section, we're going to assume that gravity is 9.8 meters per second squared or 32 feet per second squared, depending on whether we're using metric or customary units. And again, that force due to gravity is negative mg. All right, so using Newton's second law, we're going to derive some acceleration velocity models. We just need to add in their air resistance. So again, Newton's second law is just talking about the force due to gravity neglecting air resistance. We're going to bring in the force due to air resistance, and first we're going to assume that it's proportional to velocity. So let's denote the force due to air resistance by F sub r. And if it's proportional to velocity, then we're going to write that as negative kV. Here we're using a negative sign because we're talking about resistance, so it's going to be in the direction opposite motion, but we will always be assuming that K is positive. So you might even want to jot that in here, K, some positive constant. All right, so now what we'd like to do is we'd like to get the total force, which is the sum of the force due to air resistance and the force due to gravity. And so you can see we've added those there with our negative kV for air resistance and negative mg for the force due to gravity. So now if we set F equal to ma, we obtain this middle equation here, again, where dv dt is a. And we can divide both sides through by m. And so then that solves for dv dt by itself on its own. You'll notice here that we have this rho, which is just going to be that k over m, okay, stated right here. And so we're letting rho just denote that quotient. Then we can solve this by way of separation of variables to get the associated velocity function as given here and the terminal speed. Terminal speed means just what happens as t goes to infinity. That is, what is the maximum that we're going to get here in free fall. And then we can integrate once more to get to our position function or height function. So we're running through these quickly, but actually we're going to do some examples of deriving these based on this setup. And then rho has a particular name that's called the drag coefficient. So that's where we'll be running into that. All right, so let's take a look at an example here. Problem number 2 from the textbook says, suppose that a body moves through a resisting medium with resistance proportional to its velocity v. And so again, we have that dv dt equals negative kv, assuming k is positive. Part A, show that its velocity and position at time t are given by the following. So this is another example where they're giving us the solution. There's going to be no answer in the back of the book. We just want to derive this. All right, so what we're going to do is we're going to take this initial dE, which is dv dt equals a negative kv, and we can go ahead and separate variables. So we have dv over v equals the integral of negative k dt, and then we'll solve from here. So we have the natural log of the absolute value of v equals a negative kt plus some constant of integration. We'd like to solve explicitly for v, so let's apply the natural exponential function. So that's e to the negative kt plus c. As is customary, we'll bring that constant down front via exponent rules. And then normally we would drop the absolute values and pay for it with a plus minus. But because we have that overarching constant of integration C there, we're just going to absorb it into the constant. And that plus or minus would be determined by an initial condition. So I'm going to write via absorption. All right, so now we'd like to write this in terms of a generic initial condition. So if we let V of 0 be denoted by V naught, then by plugging 0 into the equation, we get C e to the 0, which is of course C. So then we conclude that our velocity is equal to V naught e to the negative kt, which is what we were supposed to show. So there's our first one. And now we'd like to go one step further and solve for the position function. So recall that velocity is the derivative of position. So I'm going to replace that v of t with a dx dt, and then separate variables. So dx on the left and the integral of v naught e to the negative kt dt on the right. All right, the integral of dx is of course just x of t. And then if you wanted, I'll write it in a different color here, you could run through and do u equals a negative kt so that du is a negative k dt, or dt equals a negative 1 over k du. Now I'm going to write this in parentheses here because I'm perfectly happy with you bypassing that u substitution so long as you recognize that you're going to kick out a negative 1 over k. So I probably wouldn't show it, and I would write this as a negative v naught over k e to the negative kt plus some constant of integration here. All right, so again, we're going to impose a generic initial condition. If we let x of 0 just be represented by x naught, then let's plug in 0 to our t values, and I get a negative v naught over k plus c. So this constant of integration is x naught plus v naught over k. And so then let's plug that back into our x of t function. I have a negative v naught over k e to the negative kt plus x naught plus v naught over k. And then we just like to work with this so that it looks more like what we have up top. So you can recognize this common factor. I will rewrite my x naught and then factor out v naught over k. And that leaves me with 1 minus e to the negative kt. And so then compare, and this does in fact look like what we were supposed to get. All right, so we have derived the position and velocity function based on the fact that our resistance is proportional to the velocity. And then we have part B here, conclude that the body travels only a finite distance and find that distance. So part of the question here is seeing if you can analyze which function we want to work with. We want to find that the body travels only a finite distance. All right, so we're not looking for a terminal velocity here, nothing to do with velocity, but rather we're looking for distance. So we want to use the position function, not our velocity function. And then we want to find that it travels a finite distance. So in other words, that this body is not traveling for eternity, rather that it's going to stop at some point. So that's some limiting behavior. We'd like to take a look at the limit as t goes to infinity of our position function. And if we're able to show that this is some finite value, then we're done. Then we've shown that it's finite, and whatever that value is will be our distance. So let's go ahead and substitute what we found for x of t. That was x naught plus v naught over k, 1 minus e to the negative kt. All right, now here remember K is a positive constant. So e to the negative kt looks like e to the negative t. If this is our t-axis, here's e to the negative t. So what's important to note here is that as t goes to infinity, e to the negative kt goes to 0. All right, had k been potentially a negative number, then that would have changed things. And so what we get for our limiting value here is x naught plus v naught over k. All of those terms are constants. So we see that this is a finite value. And that finite distance is whatever that x naught plus v naught over k value is. All right, so there's our finite distance. So these first 2 pages we're discussing how to handle air resistance, assuming that that resistance is proportional to velocity. We'd like to look at one other model, and that's when air resistance is proportional to the square of velocity. So let's take a look at what happens here and what differences arise. Here we're showing that we're proportional to the square of velocity. So we're again assuming some positive constant. That plus or minus is going to depend upon the direction of motion. So whether we're moving up or down is going to affect how we're going to set up that air resistance. And then we can rewrite v squared as an absolute value of v times v. And that gets rid of essentially that plus or minus. So remember that the absolute value of v can be written as plus or minus v. So they took plus or minus v squared, they wrote it as plus or minus v times v, and then absorbed the plus or minus by using an absolute value. All right, so we have this new setup for the force due to air resistance. And a note there about the plus or minus, that's going to depend on the value of V. And then again, using Newton's second law where F equals ma, we can rewrite A as dv dt. And we have our force due to gravity and our force due to air resistance. Here again, we'd like to divide through by m, and letting rho be k over m, we get this new differential equation. And so we have, in the case of upward motion, we know that our velocity is in the positive direction. And so we get that the absolute value just drops out, right? V just becomes positive V. And then we can write our new differential equation in this setup. And then we'll also take a look at what happens in the case of downward motion. All right, but before we get there, let's go ahead and solve this new differential equation. So this is the exact same dE that we just ended on in the previous page. And we'd like to solve this dE. We want to separate variables, and then the book is telling you how to solve this. We need to set up a U substitution so that we can integrate this function. And you'll see that our final answer here is working with a tangent function. So we're likely going to be getting a tangent inverse out. And that makes sense because we're working with a 1 plus a quantity squared there. So that tangent inverse is going to pop out due to that. So let's go ahead and separate variables. I'm going to kick all of the v's over to the left-hand side. So we have our dv on top, and we have our 1 plus rho over g v squared. And on the right, we just have negative g dt. Now I'm going to take this denominator and I'm going to rewrite it so that it looks more like a tangent inverse integral. So I'll recopy my dv, recopy my 1, and then I'd like to write it as some quantity squared. And that would make that quantity the square root of rho over g v. All right. So in seeing this, now we see why the book chose that substitution. We'll let u be that quantity being squared. And then our differential du would be just the square root of rho over g dv. If you would like to solve for dv, we're going to get the square root of g over rho du. So let's go ahead and plug that all in. We end up with a square root of g over rho integral of du over 1 plus u squared. And so that's giving us a square root of g over rho tangent inverse of u, but I'm just going to go ahead and plug in for u. And then on the right-hand side here, the integral of negative g is negative gt. And I'm going to write this as plus some constant of integration C1 because that's the notation the book uses here. All right, so we would like to solve explicitly for v. So I'm going to first multiply both sides of this equation through by the square root of rho over g. And that's going to allow this to cancel out. We'll have tangent inverse of the square root of rho over g, v, equals, we have a square root of g on bottom. That makes that a g to the 1/2 on top. So I have a negative square root of rho g t plus c1, where here I'm absorbing that constant square root of rho over g into that c1 constant of integration. Now I will apply the tangent function to both sides. All right, and I'll just reorganize here. And then finally, solving explicitly for v, I get v of t equals the reciprocal square root of g over rho tangent of c1 minus the square root of rho g t. Now, if we look up top here, what we have right now is precisely this left-hand piece. What they also want to do is to flesh out what exactly C1 is equal to. So let's go ahead and work on deriving this second portion. So I'll put a little check mark here. We got that. Now let's just assume that V of 0 is some V naught. And let's plug in 0. So that gives us the square root of G over rho tangent of C1. And so we'd like to solve for C1. First, we get that tangent of C1 equals the square root of rho over G V naught. And then finally, taking tangent inverse of both sides, we get tangent inverse of precisely V naught square root of rho over G. So I'll give that a check mark as well, because that is what we were supposed to derive. All right, so we've now found V of t, and one of the assigned homework problems is going to be to separate variables where the direction of motion is downward. The only difference here, let me grab a different highlighter, is you're going to have a minus instead of a plus. And so instead of tangent inverse here, you're going to be working with the hyperbolic tangent. So if you're not familiar with that function, that's okay. There should be formulas for integration in the end papers of the textbook, and you can refer to that, all right? But just be aware that there's a hyperbolic trig function popping out. All right, this remark at the end says, look, we're not going to do it, but we could integrate once more and then obtain the height function. So a very similar process would get you through down to this y of t function. And so we end the section just discussing that, look, we could go through and use downward motion. All that changes is that the absolute value of v becomes negative v instead of positive v, like we had up above. And so you guys will have a homework problem that is going to be very similar to what we just did on page 4. So you should definitely refer back to that when working that problem. And again, the main difference here is you're going to get a tanh rather than a tangent. And then similarly, we have our y of t function. And if you took a look at the terminal speed, remember all that is the limit as t goes to infinity of the velocity function. You would identify that that terminal speed is the constant square root of g over rho. So here again, where rho is that drag coefficient, k over m. All right, and that concludes our notes here over section 2.3, acceleration and velocity.